to talk to you all. So thank you very much for giving me this opportunity to come here and present you our results on the development of far-UVC LEDs and irradiation systems. So my talk is going to be a little bit different from all the talks that you all heard today. We're going into the technology of the lighting systems that we are using for disinfection. And this work is done with a number of partners. I would also like to mention that we'll be working with the charity. So actually I will just be talking about the technology, and then tomorrow my colleague Martina Maika will be talking more about the results in terms of safety aspects and also disinfection. So when we talk about UV radiation in general, there are really a lot of applications, and in the last years there's been a lot of talk about far-UVC, so shorter than 240 nanometers, and initially the most interesting applications were communication, so non-line of sight communication. There was also sensing of different gases, germs, and also heavy metals. So very important for the environment, and recently also because we are talking a lot about antisepsis. So the far-UVCs are extremely interesting for us, but why would we look at UV LEDs? So right now we've heard a lot about conventional sources of light, so lamps and excimer lamps, but UV LEDs give you unique advantage when you're designing such systems. Firstly, we are not fixed to discrete wavelengths, so depending on the composition of your material, you can basically also now get other wavelengths. So we're not stuck to 222 nanometers. We can move around this wavelength also and see what happens. Maybe you have some different effects, so you can combine different wavelengths. They're environmentally friendly. They're really fast turn on and off, so you can switch them continuously. There's no problem. They're electronically dimmable. They have really compact form factors, and this allows you to basically design a light source based on your application. So you no longer are restricted to particular forms that you have in your traditional lamps. You can now make a system that is curved, or you can have it only in particular areas where you want it to be illuminated and not everywhere. So this gives you really a lot of freedom when you're designing your systems. They are robust, and ideally they have also very low operating voltages. So you could think that you could also use them by solar-powered systems or also battery-powered systems. But currently we have some disadvantages or some challenges that we still need to address when it comes to UV LEDs. And the first is that they do have very moderate efficiencies right now. They have also moderate lifetime, so we're talking a few hundred hours, and they are fairly expensive. But I hope I can kind of convince you it is still a very interesting technology. It's a cross-sectional technology. It is not only interesting for antisepsis, but also for many other applications. So when you think about the development of a UV LED, you need to think of the whole process chain. So you're starting from the heterostructure of the device, which actually when you grow the crystal structure of an LED, and it's not just like one material, it's a number of layers that have to be chosen very thoughtfully so that you actually can get a high efficiency of your device. Then you go on to the chip design, so that's when you put in your metal contacts to make electrical contacts to the LED. And also over here, it is really important how you design these chips so that you can improve the efficiency and the lifetime of the devices. Then you go to packaging of the device. Here you want a package that can easily remove the heat that is generated in the LED. You also want a package that can form the light that is emitted. So basically you get the radiation pattern that you want for your application. And then you go on to the next steps, which is basically module design or system design, and then for your complete application. So over there, you work very closely with your application field and see what they really require, and then define and design your system accordingly. So you basically have to work on each of these steps in order to improve the efficiency, lifetime, and to reduce the cost of the system. And at the Fund Brown Institute, we have the unique opportunity that since we have epitaxy facilities in-house, we have processing facilities in-house, packaging, and also system design, we can actually work on all these aspects during the UV LED development. And that gives us also a unique advantage to directly design LEDs right from the beginning for the different applications that we need them. So I'm going to give you a few examples along this process chain today, and I will start with the LED heterostructure. So over here, what you can see, I think you've seen this graph. People who know UV LEDs have seen this graph multiple times. It's always updated by Michel Kneissl. And what you see over here is the external quantum efficiency of the LEDs at different wavelengths, and basically based on their wavelength. And the external quantum efficiency is related then to your wall plug efficiency, which is basically the amount of optical power that you get out of the system divided by the electrical power that you put into your system. And the external quantum efficiency is then directly related to this value. So basically, the worse that your external quantum efficiency is, the worse your wall plug efficiency is going to be. And you see that when you're in the UVA region, so you have nearly like 80% efficiencies, you have very efficient devices, but as you go to shorter wavelengths, the efficiency drops very drastically. And if you go to the far-UVC wavelength, it drops even more. So you have like around 1% external quantum efficiency. So most of the energy that you put into your system is going to be converted into heat, and that's why you'll all have this big heating problem when you have far-UVC or UVC LEDs. On this graph on the right, basically we have kind of plotted the emission powers of commercially available LEDs right now. And this is not the latest values. There might be some presentations later on today that have some better values out there. But this is what we could find on the internet. And also here you can see very clearly that in the far-UVC region, we have only a few milliwatts that we're getting out from every LED chip. So the efficiency is really low, the power is really low. And also very interesting, there are very, very few companies or research institutes working on LEDs that are basically emitting in this wavelength. So we have low power and we have only very few manufacturers of LEDs in this wavelength. And to understand why do we have these low efficiencies, you need to look at the LED structure. And over here we have a schematic of a UV LED with the different layers in such a structure, and you start normally with a substrate on which you grow the different semiconductor layers. And here you can use aluminum nitride or sapphire is what we use in our case, and it needs to be transparent because that is where you're going to extract the light from the LED in the end. Then you basically have an aluminum nitride layer on the sapphire, and since they have different lattice constants, there is a tendency for defects to be formed at this layer. And therefore you need to reduce these defects, because these defects can then propagate into the active region of the LED and act as traps, so you won't get any light out of these carriers. So you need low defect densities. And then as you go from aluminum nitride to aluminum gallium nitride, you have to make sure again that you have some kind of strain management layers, because you don't want any new defects to be formed while you're continuing to grow. So you have some strain management layers. And then you come to a current spreading layer, which is the end contact layer. There you want to have really high conductivity in this layer so that you have a low operating voltage of the device. And then you come to the active region, which is basically quantum wells with indium aluminum gallium nitride quantum wells. And here it's really important that you look at aspects that the carriers are really confined in the region. You have also sometimes polarization of the light, which I will explain a few slides later. So you need to control all of this in this active region. And then you have the N, the peak current spreading layer. So basically, you want good conductivity here. It's really difficult because now you have like high aluminum gallium nitride, so you have really difficulty to make conductive layer over here. And what you also would ideally like, you would like this layer to be transparent, because if it was transparent, then any light that is emitted in this direction, if you have a mirror over here, you can reflect it out of the system. So that way you can also then collect the light which is emitted towards the P contact. So that's what you want to do. That's really difficult to do. And then you have the ohmic contacts, so the P ohmic contact and the N ohmic contact. And once again, you need really good contacts so that you have low voltages of your device, and you also, in the best case, you would also like to have UV reflective pre-contact so that you can extract the light out of the LED. So I can show you there's really a lot of challenges, and we and other groups are working on each of these layers to try to improve the external quantum efficiency of the LED. And here you can see this is a real LED structure that we are using for our far-UVC LEDs. We basically divide our growth into two parts. At the bottom we have our templates, which is sapphire and aluminum nitride, and then we have a LED heterostructure on the top. For the templates, we are using aluminum nitride sputtering system, which you can see here. It's for 9 2-inch wafers, and then we have a 16 times 2-inch wafer high temperature oven to anneal the sputtered aluminum nitride layer, and then we regrow using MOVPE, another aluminum nitride layer on it using an 11 times 2-inch planetary reactor. And then for the LED heterostructure, we use a 6 times 2-inch closed coupled showerhead reactor for our system. So like I mentioned, why is the substrate, the template so important? Like I said, we are growing on sapphire, which is transparent in the UV region, and if you grow aluminum nitride on it, because of the lattice mismatch, you're going to have defects in the crystal. And some of these defects, they bend out, but some of these defects, they continue into the LED structure and actually come into the active region, and there they act as traps, and then you will not have any light produced in the LED. And what you can see over here on the right-hand side is the quantum efficiency, again the efficiency of the device based on the number of threading dislocation density, so the number of defects that actually go to the active region. And you see that if you reduce the number of threading dislocation densities, you can get a very large increase in the efficiency of the devices. And for us, the number 10 to the 8 is like an important number, because if you can reach there, then you already have quite a high internal efficiency. So there's a very stark increase as you go from 10 to the 10 to 10 to the 8. And therefore, we have tried and developed many different technologies on how we can develop such substrates and templates with a lower threading dislocation density. And I'm not going to go into detail into the slide. I just want to give you an idea of the different approaches that we have used to actually get low threading dislocation densities. And so basically the first way is a very simple growth, MOVP growth of aluminum nitride on sapphire. It's good because you can reduce the threading dislocation densities, but you need to go to very thick layers in order to get a lower threading dislocation density, and then that leads to cracking of the layers, and that's not good for your device. So what can you do? What we have tried is sputtering a thin aluminum nitride layer or MOVP layer on, of aluminum nitride on sapphire and then annealing it. This helps us to reduce the threading dislocation densities while still having thin layers. We don't have cracking. What works even better for us is if we do like a double annealing. So we first sputter aluminum nitride, we anneal it, then we do MOVPE aluminum nitride and anneal it again. And that's basically the values that you see here. So we can get in the 10 to the 8 region and still have reasonable thickness of aluminum nitride. And this is quite a cost-effective method because you don't need any processing. You just need to sputter aluminum nitride and then go with MOVP. So this helps the cost to remain low. Another method would be to actually structure the layer, as you can see here. And you can use this also then to basically reduce the dislocations that are created in the system because of these structural patterns over here. You come to a low threading dislocation density, again with reasonable aluminum nitride thicknesses. What advantage this gives you is basically now you have some structures in your system. So this will help you to basically scatter the light out of your LED structure. So this is quite helpful when it comes to the extracting light from your LED. The disadvantage of this approach, of course, is although you get a good and low threading dislocation density, it's quite expensive because you need to go now through a whole lithography process to structure the layers. and of course then the costs are quite high. So using this as one example of how we try to improve the performance of the LEDs, I would like to show you what is the status of the LEDs that we have right now in the far-UVC region. So the wavelengths that we have been focusing on are 225 nanometers to 230 nanometers, and then the second wavelength is between 230 to 235. And over here you can see some examples of how the spectrum of the LED looks at these two wavelengths. So at 228 nanometers, we have around 10% parasitic luminescence. So unlike conventional lamp, we don't have a discrete emission wavelength. We have a wavelength with a full width, half maximum of around 8 to 10 nanometers, but you have also parasitic luminescence at longer wavelengths. But if you remember, there's a logarithmic scale, so but it is, for example, for disinfection of skin, this could still be a problem. But for many applications, the big difference in the intensity is no problem. This is 10%, like I said, for 228 nanometers, and at 234 nanometers, we have a parasitic luminescence of around 2%. If you look at the powers of the LEDs, so at 226 nanometers, at 200 milliamperes, we have 2 milliwatts of output power, and at 233 nanometers, at 200 milliamperes, we have 10 milliwatts of output power. What is not very encouraging initially when you look at it is the lifetime of the LEDs. So over here we have plotted the output power of the LEDs over operating time. And you see that in both cases, for the 228 nanometers as well as the 234 nanometers, within the first 50 hours of operation, you have a very drastic decrease in the output power of the LEDs. And then the decrease is it's slowed after the first 50 hours approximately. So what we do for our applications is basically we burn in the LEDs, so we say, okay, we're going to accept this 50% or 60% decrease in the output power. We burn in the LEDs for 50 hours, and that helps us to basically increase the lifetime of the LEDs. So then if we start from the 50-hour point, then we get lifetimes of L50 around 1,000 hours. So again, this is something that is then helpful for the applications, because then you have more stable operation of the LED during the application. So that was one example, basically what we did with the heterostructure design, and now I want to show you something with our chip design, what we did to try to improve the performance of the LEDs. So when you have this is a typical LED structure over here in the middle, that's where the light is generated in the device. And what happens is, in an ideal case, you would consider the light that's generated in the active region to be isotropic. That means it's emitted in all directions. But this does not really happen in the LED. So because nitrides is a Woodside structure, you have some polarization of the light. And the light could be TE polarized. It's like if it was fully TE polarized, it means basically the light may be emitted in the top and bottom direction. And if it was fully TM polarized, then basically the light would be only emitted laterally. And you see that at longer wavelengths, so at around 260 nanometers, most of the light is actually TE polarized. So that's really good when you want to remove light from the LED, because it's anyway being emitted only in the top and bottom direction. The problem is, as you go to the far-UVC region, you're getting more TM polarized light than TE polarized light. That means it's becoming even more difficult to extract light from the LED, because it's basically being emitted laterally. So it could be firstly absorbed again in the LED structure, and secondly, it could also undergo total internal reflection and cannot come out of the LED structure. So basically what we need to do is try to get this light, which is actually being emitted laterally, to come out of the system. So we need to direct it down and out of the device. And to do that, what we are using is micro-pixel LEDs. So basically, we are reducing the size of the LED to a much smaller size. So basically, a size of 1.5 microns. Each of these LEDs, you could consider them to be micro-pixels with an array of 4 microns. And then we have covered the system with silicon oxide sidewalls, which we have sidewalls which are 45 degrees, and then we put an aluminium reflector on the system. And now what happens is light that is actually emitted laterally gets reflected because of this aluminium reflector, and then will come out of our device. And so we can actually then improve the efficiency of our LED because we can collect more light out of the LED. And yeah, and what you can see over here, the amount of light that we can collect from the LED is dependent on the size of these micropixels that we have, so these micro LEDs. And if you go to smaller diameters, basically then you can extract more light of the LEDs because that's less distance that the light can actually travel in the system. And a very interesting effect of this is also that if you look at the far field of such LED chips, so typically if you didn't have these micropixels, you just had these large LED structures, then you would have such a form with these typical rabbit ears in the far field distribution. So actually the maximum in the intensity at the angle which light is emitted is actually not at 0 degrees, but actually at 30 degrees. But with these micropixels, we now have a more Lagrangian pattern. So this is also very promising if you want to couple the light into a fiber for different applications. So this is one of the good side effects of this design. And here you can see now the output power we have with these micropixel LEDs. We have 18 milliwatts and 250 milliamperes. So we already been able to nearly double then the output power by using this structure. And now we have a peak EQE of 3%, which is also right now, I think, the record for. So what can we do now in terms of the package? So that's how we get more light out of the LED itself. How can we now basically form this light that we're getting from the LED? And we do that by designing different packages. So here you can see the radiation pattern for different packages. So basically you have an open chip without any package, without any lens. Then you have this form which I showed you earlier. Then basically you can use an aluminium reflector in the package to get more light out of the system. So then you get a more directed light emission. Then you can also combine it with different kind of lenses. So here there's 2 different lenses, and based on the lenses you can get different viewing angles for the LEDs. So you really need to think then, what is your application? What would be the best radiation pattern for this? What would be the best viewing angle? And based on that, you can then choose the suitable package. So at FBH, we have designed different packages that would be then used in different applications. So then let's go to some examples of how we have used and designed LED-based irradiation systems for different applications. And the first application is, of course, UV antisepsis. I don't need to go in and explain to you all about how it works. What is really important, however, the diagram on the right side, that depending on the wavelength, you're going to have different penetration depths in the skin. And therefore, like I earlier showed you, the LEDs do have parasitic luminescence, so it's really important for us to cut out all that wavelength, this longer wavelength, otherwise you're going to have deeper penetration and maybe damage in the skin. So to do that, basically we have designed a hafnium oxide and silicon oxide DPR bandpass filter to suppress this long wavelength radiation, which you can see here. But what you notice, we're also then actually removing a lot of the intensity of the LED, and we find that these filters are really dependent upon the angle of incidence on the filter. So basically, if the light hits the filter at larger angles, you're going to have less light which is transmitted to the device, and you need to have more collimated light in order to have a high transmittance to the device. And to do that, we basically looked at our different packages and decided that the package with an aluminum reflector and a planar convex lens, what you can see here with more collimated light, was the best option for the system, and therefore we could increase the total transmission from 26% when you did not have this collimated chip emission to 46% with collimated emission. And we built such an irradiation system based on 120 LEDs in an 8 times 8 centimeter system over here, and we use active water cooling, and we can also adjust the LEDs, the emission from the individual LEDs, so that we get a very homogeneous emission. So we have 92% uniformity over 7 centimeter diameter. And these systems were then used with the Charité and with University Medicine Greifswald to do some tests on MRSA, where we could show that we could inactivate MRSA with the 230 nanometer LEDs without causing any significant damage. More information on these tests will be shown tomorrow at Martina Meinger's presentation. So what can we do next? The LEDs are small and they have this compact form factor, and so what would be the ideal way to use them is, one, we could use them basically to disinfect wounds on the human skin, and also mucosa in the mouth or in the nose. And in order to do that, basically you need to make a miniature system, and as we all know right now, one of the big problems we had is removing the heat from the LEDs, and so we have designed a miniature system over here. It is a 4.5 millimeter diameter. We did this with 3D printing in stainless steel, and we were able to, for a power loss of 1.6 watts, we get only 35 degrees Celsius, and total thermal resistance of 7.5 Kelvin per watt. And you can see over here it's just basically an LED then on the system, and we can very effectively then remove the heat from the device. So that would be like the next step in terms of irradiation. Another application is gas sensing. In the far-UVC region, actually, there are many interesting wavelengths for gases such as nitrate, ammonia for nitrogen oxide, sulfur dioxide and nitrogen oxide. And currently they use electrodeless discharge lamps, but as you can see over here, the 226.5 nanometer LEDs that we have already have the intensity which is good enough to use this then in such sensing applications. And we have worked with partners to prove that using far-UVC LEDs we can detect nitrogen oxide in the ppm range, and we're also working with partners to make multiple wavelength LED modules, so at 226, 275 and 405 nanometers, and the next step would be then to put this all into a package together. Yeah, so that brings me actually to the end of my talk. And I hope I was able to show you that at the FPH we have taken a number of steps at the different stages of processing UV LEDs to increase the power of the devices, and that with the LEDs we can make very innovative irradiation systems for applications like UV antisepsis and gas sensing. Thank you.